speakers. Today we are joined by Brandon Van Leer, Chris Stevens, Hsiang-Han Tseng, and Zhao Liu. And with that, I'll hand over the stage to Zhao.
Oh, actually, I
Oh, to
think
share
it's
screen. And Brandon. Brandon
all
will
right.
start speaking, but then Zhao will share. Thank you.
All right, great. Let me go ahead and share here. Apologies.
Okay.
Um, Zhao, I think you're going to have to share for whatever reason. My deck is not showing. It says I have to quit. So if you could bring that up, that would be great. Apologies.
It's
All right,
not.
great. Thanks. All right, you can go ahead and go to the next slide. So today we're really excited to talk to you about some of the materials characterization techniques that Thermo Fisher is working on to advance battery science. So we have three focus areas today. I'll kick off with a short introduction to Thermo Fisher Scientific for those of you who don't know about the company, and introduce you to what it is that we're doing. And then we'll transition into our three focus areas, which is using electron microscopy for advanced characterization of reactive materials. And then we'll transition to Chris, who's going to walk us through how we're using scanning electron microscopy, specifically for elemental and crystallographic characterization. And then last but not least, we will transition to Hsiang-Han, who will talk about using XPS for surface characterization in battery science. So if you could transition, thank you, Zhao. So, at Thermo Fisher, our mission is really to help our customers make the world healthier, cleaner, and safer. And there's really no better tie-in for battery science into the cleaner part than battery characterization. And so, over the past several years, we've really devoted a lot of our R&D dollars to help generating and creating new workflows for battery science and characterization. Next slide. The company itself is really focused on advanced characterization for not only research and development, but for quality control as well as failure analysis. Together, we're 120,000 colleagues across the globe, and more than 77,000 of those folks are really focused on research and development. As you can see, we also generate quite a large sum of revenue, and out of that, we spend about $1.5 billion a year that goes back into R&D to develop new solutions for our customers. Next slide. Now, if you think about where we play in the battery value chain, there's many different types of solutions that Thermo Fisher Scientific offers. And you can see they're ranging from R&D all the way through end of life and recycling. There are different types of characterization and solution capabilities that Thermo Fisher Scientific offers. Today, we're going to be focusing on electron microscopy and spectroscopy specifically. And the focus areas that you'll see today were really around research and around impurities analysis and characterization. Next slide, Joe. So, in terms of what we see happening in the battery field, there's really a lot of things going on, as you all are well known. But what we see right now for battery manufacturers is there's really a shift to lower cost chemistries, but still improving manufacturing capabilities. Also, there's a huge focus on scale and yield optimization, and that's really been driven through using automated techniques like automated impurities analysis. And then last but not least, we can continue to see the regionalization of supply chains across the globe, where folks are sourcing materials for manufacturing locally as well as doing vertical integration. Next slide, please, Zhao. Just quickly wanted to highlight, some of the capabilities that you're going to see today. This is just spans across electron microscopy and, as I mentioned, surface analysis with XPS. Of course, we have many other characterization techniques. But today we're going to talk about working with reactive materials as well as elemental and crystallographic characterization as well looking at surface chemistries with XPS. Next slide. As I exit the introduction and transition to Zhao, these are our three focus areas, as I mentioned. We're going to talk about how we use inert gas sample transfer and our Clean Connect technology to be able to produce the highest quality results for reactive materials. And then Zhao will transition to Chris, and we'll talk a little bit how we're using our analytical solutions in SEM to really understand impurities analysis, elemental characterization, phases, crystallographic information. From there, Hsiang-Han will talk a little bit about how we're using XPS to really probe the surface and subsurface for chemistries, whether it's looking at contaminants or really trying to understand what's going on right at the surface of those reactive materials during battery processes. So with that, I will say thank you and thank you for joining today. We're happy to answer questions that you might have about our techniques and solutions, and I will pass it to Zhao.
Thanks, Brandon, for the introduction. Hello, everyone. So my name is Zhao Liu. So for the next 15 minutes, I will discuss about one of the very critical challenges when you're doing the image and the characterization on the battery materials is how we be able to establish or standardize the workflow that be able to provide a repeatable, reliable result when imaging and characterize the battery materials. Um, so here we can use a lithium metal battery as an example because as a promising next generation batteries, there's a lot of development effort need to happen, which require advanced battery characterization, especially in the electron microscope part. So as you can see in the left, as a schematic of the lithium metal battery, it composed of three major parts. It will have a thin lithium, ultra thin lithium metal as anode with a separate or safe electrolyte. Depends on if you use a liquid based electrolyte or solid state battery. So you will have either solid or liquid electrolyte, which separated by a separator. And finally, you will have high performance cathode side that overall the design will deliver high energy density with premium performance. Um, when you develop those batteries, there's all the materials facing the challenge because they are very reactive. If you look at the one and two, the cathode and anode side, the morphology structure you're interested in will be the morphology itself, the composition or the crystallographic information on both sides of the materials. And the technique you're using for the electron microscope part cover the ACM, FIB, ACM, TEM. And then if you look at the interface, which is now 3 and 4, that corresponding to a solid electrolyte interface and the cathode electrolyte interface, the major characterization method is actually the transmission electron microscope. And the feature of interest including the morphology, composition, the distribution. Because most of the materials itself are very reactive, it actually will be impact major the two different probe. One is we call the environmental probe that is related to the moisture or the oxygen in the environment. Another one is the electron or ion beam when you're actually doing the imaging or the sample preparation to react with the materials that can cause in the sample could potentially be damaged. So the question or the challenge being how we be able to preserve the sample at a native state when you have the external probe exist. In order to address those challenges, let's first look at the sample journey from the glove box all the way to you do the atomic imaging inside of the electron microscope. So the sample will starting from the glove box from the left, then you will move to the ACM and the 3B ACM to do the imaging or the lamellar preparation. Then you will move back to the glove box. You will exchange to different transfer holder. Then you insert to the TEM to do the final atomic calculations. So the question would be where when you do the transfer between the different devices, how you be able to do the transfer, and also in the different instrument, does the cryo is always needed. And then currently in the practice in the field is that both the transfer and the cryo condition used in the instrument is not standardized, meaning that different group using different protocol to do the transfer and the characterization process. That causing the result is not very consistent or even repeatable well. And then we also see that although the cryofib and the cryo-TM being increasingly being adopted to characterize the lithium metal battery samples as examples, um, it's not very consistently being used in that way. And finally, the being and materials interaction is not well controlled because the team will thinking that um, if there is a materials is already being protected under cryogenic temperature, then other parameters not necessarily be tracked. So in the following sections, I will talk about what we think the best way to do the characterization to on the reactive battery materials. Because of the different needs to understand the morphology, structure, and composition at different length scales, we summarize the workflow into three different major sub workflows in this way. On the left, you can see the most simple and straightforward one will be the 2D microstructure characterization that involves the sample transfer between the glove box to ACM or dual beam. And then if we want to do the characterize the materials in the cross-sectional view and in the large scale, for example, you want to look into the sample cross-section in the millimeter scale, then you will involve broad ion beam for the sample preparation. And finally, if you want to look into the microstructure at the atomic scale, you need to transfer from the sample from the glove box to the dual beam to do the sample preparation. Then you all the way need to transfer to DEM so you can enable the atomic scale characterization. So let me go through each workflow one by one. The first workflow is a 2D microstructure characterization that indicate you directly transfer the sample from the glove box to the dual beam to do the ACM to do the ACM imaging characterization. The key component that enable this workflow is a device called Clean Connect. So as you can see on the left is a transfer unit that have a capsule that will be able to store the sample in. And then the transfer unit be able to attach to both the microscope side and the glove box side. And inside of the capsule, you will have the sample sitting in a positive argon environment where that will be mimic the situation the sample is actually sitting inside of a glove box. This way will be well protected sample compared to the vacuum transfer because you have limited risk of the leaking issues when you have transfer the samples. On the right is just a comparison the sample using lithium metal during the transfer with or without clean connect to protect the sample. It's obvious the result that if you don't have a sample transfer protected by the argon environment, your sample is severely damaged. And on the bottom left shows if you do the clean connect transfer, your sample still have a very pristine surface and a clean surface. And more than that, sometimes you need storage samples in the transfer unit and from, for example, your lab all the way to your microscope room. They take some time during the transfer period. And during this case, we store the sample in the in the Clean Connect for over 1 hours, and you can still find that the sample is well maintained. That means under the positive argon environment, the sample is well maintained, the sample integrity. Then let's look in the second workflow, which is involve broad ion beam system that can do the large area cross-section preparation. For you who is not familiar with the technique, so broad ion beam technique is a technique that you can see on the bottom left as a schematic view how it works. Is a technique actually prepare large area cross sections. And as you can see, you will have the orange as a mask with your sample in a greenish color and as an example, and then your sample will be higher on over the mask where when you're using the broad ion beam as a red arrow actually spotting away the materials, everything above the mask will be removed so that you can get a large cross section. On the right shows the ACM imaging overview of how the cross-section prepared. As you can see, after the broad ion milling process, you will have a very large sub-millimeter range of the cross-section well prepared that be able to do the microstructure analysis. And you can also zoom in to find the quality of the preparation is really good. So a lot of details is actually be able to capture for your ACM calculation in this way. Um, Again, we can also compile the sample transfer with or without a clean connect. As you can see, even with a cathode sample, especially if you're dealing with a high nickel MC samples, you're facing the challenge in the materials is still very sensitive to the moisture and the environment. So if you transfer without a clean connect after polishing the surface of cross section, you will actually suffering a lot of contamination on your cracks on your particles, as you can see on the right. So that will result in the incorrect calculation result. So the next I will show you the most complicated but the most critical workflow is the nanoatomic scale calculation. As you can see, the sample will go through the journey from the glove box all the way to the TEM, and it has multiple transfer steps. When you transfer from the glove box to the FIB-ACM, the sample will have a risk of exposure to the environment causing damage. Inside of FIB-ACM, the ion beam and the materials reaction can cause the sample damage as well. And then when you transfer from the lamella from the glove box to the TEM, different transfer method could also cause the contamination on the surface. As you can see here, the ice crystal grows on the lamella. And finally, in the TEM, depends on what type of dose you are working on the samples that can further creating more damage on it. So there's multiple way you can go runs. So the question is how we be able to provide the guidance so you can properly handle the sample from the transfer to the imaging to get the right result. So maintain the sample in the native state. So the first step is analyze the lithium metal inside of FIB-ACM. The image on the left shows if you use a gallium fib to to milling the sample at the room temperature, because of the gallium lithium will form the stable phases during the alloying process. It actually can damage the lithium metal samples here and form a lot of porosity, which the preceding state have been changed. So in these cases, you have two parameters. One is the reactivity between the lithium and the gallium. Another is actually the heating damage on the samples. So instead of using gallium at room temperature, we can use a plasma fib, which have an inert, for example, xenon source to polishing the sample. And as you can see in these cases, we do not see any reactivity between the lithium and xenon, and the heat damage is not sufficient enough to ruin the surface. That indicated in this case the chemical reactions actually be the major factor that impact the structural changes during the 2D characterization process. And we will recommend that if you only care about the 2D cross-section analysis, if you're using the PFAB as a tool, the room temperature characterization is enough to get an accurate result in these cases. However, if you want to do the lithium metal lamella preparation, the situation changes. On the top, it shows the process of the prepared lithium metal with a plasma fib, but at room temperature. As you can see that on the top right, the lamella actually being severely damaged in the end. That is because once the sample is getting smaller and smaller, the thermal conductivity is getting worse. Your sample is no longer to surviving and handle the heat damage on the sample and causing the damage on the samples. So in these cases, to validate the process, we do the full cryo process for the lamella preparation, which is showing the bottom. And in these cases, the sample is well protected, you can get a high quality lamella if you go through the full cryogenic process during the preparation of the lamella inside of the FIB-SEM. Then we are looking for the next step is about from the sample transfer from the glass box to the TEM. Even you have a good high quality lamella, it still can go wrong. So this just showcase an example where if you use either cryo transfer holder or the cooling holder to do the transfer process, the cryo transfer holder meaning that you will your sample will sit in the liquid nitrogen tank, and you transfer sample through the cryo holder transfer holder to the TEM, and then because of the moisture can attack the cold surface, it will form the ice crystal, as you can see on the line A here, that there's a lot of ice crystal formed on the samples. Well, if you use a cooling holder with a glass bag to do the transfer, because there's a short exposure time between you remove the glass bag and insert to TEM, even a few tenths of seconds, you will have the contamination on the surface. So what will be the recommended solution in these cases? In our experience, we found that if you have an inert gas transfer holder where the holder can do the inert gas transfer with the cooling function, when you insert it into the TEM, you will get a very clean surface that you can see the row C over there. And if you can be able to get a very clean and the non-contaminated the lamella in the TEM, you even can get atomic resolution of the lithium without put the sample in a cryogenic temperature. So the question is why in the past experiment the science engineer always need to put the TEM into cryogenic temperature to minimize the damage. One of the major reasons is actually because of the ACI component, which is more sensitive to the beam damage. So in these cases, we actually use a sodium carbonate, which is one of the key components in a sodium battery as ACI. In these cases, to do the analysis. The figure on the left shows at room temperature and cryogenic temperature comparison and how does the dose impact on the sample. As you can see, at room temperature, if you get the total dose over to 150 electron per angstrom square, you already have severe damage on the sample. Your sodium carbonate will turn to different materials, and there's a lot of damage mechanism also happening in the meantime. The cryogenic temperature, however, can give you a little bit more room for the dose to be able to endurance on the samples. However, if you still reach out to more doses on the samples, you will still damage sample. That indicates the cryogenic condition can actually reduce the beam-induced damage. However, dose tracking will be still very critical because it's not like if you have a cryogenic temperature, you are already worry-free in these cases. So in summary, in my presentation here, I just showcase IGST workflow is very critical for the sample transfer. And during the FIB-SEM, you need to really consider the chemistry and temperature as a parameter that it can cause the sample damage. And finally, in the TEM cryogenic temperature, TEM is not always the only answer. You also need to be very careful about the dose in the characterization part. So I will pass to my colleague Chris to talk about analytic techniques in the scanning electron microscope to understand the battery materials. Chris, the floor is yours.
Thank you, Zhao. So yeah, following on, I'm going to be looking at the SEM-based analytical techniques. So what I mean by that is adding various types of detector to the electron microscope to give more layers of information and a better understanding of the battery material. So on to the next slide, please. So the battery materials themselves, if we step back, we can say they are intrinsically heterogeneous. So we mean that spans multiple phases. It's a kind of a complex and a porous architecture. You've got multi-phase structures, and you often have trace level chemical variation that these can basically influence the performance. So the challenges that we have are basically to connect the local material features with the cell level performance. And as you can imagine, this would be quite complex with bulk measurements alone. So the SEM-based analytical technique kind of addresses this because it's providing spatially resolved information on composition, morphology, porosity, the cracking, and the grain structure, and it's doing this on the relevant length scales. So it means that we can identify the chemical inhomogeneities in the electrodes, we can detect the contamination and the trace elemental segregation, we can quantify the cracks and the pore networks, and we can resolve the microstructural features that might govern the transport or the mechanical stability. So this matters because if you think about it, the degradation, failure, and performance loss really will originate on the microscale, and then this will affect the overall materials development. So then lots of the continual development will then depend on having this good characterization. So let's go on to the next slide, please. And looking at the sort of the three techniques that we're going to cover today. So the SEM, the top point, we're looking at what we call the ChemiSEM technology. So this is an integrated SEM EDS workflow. So we're going to look at what this is and the information that we can bring. So this is really looking at rapid chemical screening. It's going to reveal compositional contrast and really identify trace phases, and it can do this over broad sample regions. Second, we have perception. So this is for automated analysis of particles in particular. So this is looking at the contamination detection and its classification, and it's doing this over continual, almost 24/7 operation. Finally, we have the TruePix EBSD. So EBSD being electron backscatter diffraction, and this is providing localized structural information. So this itself has information on the morphology, and this crystallographic insight enables you to basically have this localized information of what that structure is doing. So the analytical techniques in general enable you to combine all of these together to really understand what is happening on the microscale. So with that, can we go to the next slide, please? So EDS, I'm going to start with this is energy dispersive X-ray spectroscopy. So what we're doing is we're analyzing the characteristic X-rays which are generated when the electron beam itself interacts with the sample. So this enables the user to qualify which elements are present and then quantify how much of each of those elements. So the figure on this on the left kind of shows how this works. So the characteristic X-ray, this is what we're interested in, and this is what is sort of occurs when a core electron is emitted, and then the characteristic X-ray, as a core electron is ejected, higher energy electron will fill the void, and then this will emit this X-ray. Because each element essentially has its own unique set of X-ray line positions, we can use this to determine what is present. So within the material itself, this matters because you then get the localized composition, so we can see precisely which elements are there. We can map these spatially, so we can see how that distribution will vary through, say, the electron. We can look at the individual contaminants, and this can go down almost to trace level, but also we can see individual compositional gradients, and that'll also tell you additional things about how the material is performing. So in the bottom right there, you'll see a typical example spectra that you get. So this essentially shows each of the elements that are present, and then you can quantify exactly how much of those are present, and you can do this down to essentially nanometer scale. So on to the next slide, please. So here I want to sort of tie this through to some of the sample preparations itself. So as I mentioned, you'll get quantitative elemental composition, and depending on that sample preparation, you get something maybe 2 to 5% relative accuracy of this. But there's various things that you're going to want to consider, right? And what I'm saying with this is the composition itself will really depend quite a lot on how the sample itself is prepared. So as the sample interacts with the surface, you get these interaction volumes, and ideally the sample would be homogeneous within that region. So typically some of the techniques that we do is to go down to maybe a lower primary beam energy. That would give you a smaller interaction volume. And we also do quite a lot on the processing side to make sure that the quantification routines can be as accurate and reliable as possible. But if you just click on here one, please, Zhao, what you'll see is the linking to the clean mill story. The sample itself, or the results that you get, are going to be really tied to the sample preparation itself. So because we have porous multi-phase electrodes, the interaction volumes can actually end up being quite complex and often will be non-homogeneous. So you have rough surfaces, smear, redeposition, uneven sections. This is all going to complicate it. So if you use something like the clean mill, so the broad iron polishing, will really help here because it will give you that clean, well-defined cross-section. And then from there, you can then proceed to do the reliable characterization. So what we can kind of say is for the battery material, the sample preparation really is that foundation, and then we can build onto that for the analytical results. So on to the next slide, please. So going a little bit further, one of the techniques we've introduced is what we call chemiphase. And this is loosely based on a so-called PCA or principal component approach. So if you think about it, when you analyze a map over a sample, every single pixel in that map will have a full spectrum behind it. So it's kind of a complicated multi-dimensional data set. And using a PCA or principal component type routine, you can really reduce down the complexity of that. And what it is doing is essentially grouping together the pixels with the same composition. And it's able to do this from relatively few X-rays in any given pixel. And then the software itself will assign each one of these to a particular phase. And then from that, it gives you a really clear idea of what the sample it looks like. So let's kind of look at this in practice, and onto the next slide, please. What you will see is what something typically would look like. So on the left is a typical, in this case, backscatter type image from an in-lens detector. And on the right, we can sort of understand what we have. So you have the main sort of NMC region, you have the aluminium layer, you can see the binder, but you can also see two little green regions that the system has automatically identified as being different. So as you click on one, what you'll see here is the system is able to identify from those regions that you're going to have a slightly higher, in this case, nickel composition and a lower cobalt content. And in this case, this tells you something about the material itself. So this, in this case, it's a nickel-rich cluster, and this local inhomogeneity isn't really obvious from looking at the SEM image alone. So the system is able to really identify features on the chemistry that you would not see out of the image. So what we would say is these are the sorts of things that would accelerate the degradation of the material. It would contribute to the performance loss. And what we're able to do is identify these automatically. So on to the next slide, we'll sort of see a little bit more complicated version of this. So in this case, we've got different types of contaminants in there. And in this case, you'll see that the spectra from each ones of these are going to look slightly different. And why this looks quite good, just click forward, is you'll see that kind of in all cases, you're going to have quite a big background of the matrix itself. So this is the nickel, the manganese, the cobalt are going to be present in all of them. But in one, you have a copper zinc rich phase. The other is a zirconium phase. So just again, looking at the image itself, it would be very difficult to identify these. But in terms of the automated routine, it becomes really, really clear and obvious that these are different regions that you want to identify those. So this is how we'd look at it in a screening. Now we're going to look in the next slide on some automated particle analysis workflow. And this is where perception really comes in. So this is if you want to identify the contaminants, but you want to do it many, many, many thousands of times per hour, and you run this in a purely automated process. So what perception does is you segment based on features. The system will then measure automatically every single particle in there. It will, according to a recipe, do a full EDS analysis. It will classify and report according to a recipe, and it will do this again and again, many thousands of times in an hour. So just to see a flavor very briefly of what this is looking, you'll see a video on the next slide. And what you may need to see, sorry, go on to the next slide as well, please. What you'll see is basically the impact and the impurity itself is really going to see and affect this process. So if you just click into the next slide, we might just see this running automatically. And as you move into the video, you'll see that the perception software itself, in the left, you'll see a huge number of individual particles. You would load in a recipe, and then the system would automatically acquire individual particles, and it does this according to a recipe. So we move through. As we look at the video itself, this is now what the automation looks like. So it is automatically classifying. You can view the morphology, and then you get the chemistry of, as I say, thousands of times, and then you can build up the report of this. And you'd run this routinely, as I say, up to 24 hours a day. So full automated throughput. So in the next slide, you'll get a flavor of the idea of what the reporting would actually look like. So once you've acquired the recipe, there's a huge amount of information available for every single pixel or every single particle in the image. You'll characterize automatically everything that is in there, and then you would send this into a report, and then you would classify it according to the ISO standard, and then all the information that you need is there. And because this is in a predetermined recipe, you can then easily transport this between many different systems. So this is how you would use the automated particle analysis and really use that to complement the ChemiSem and the ChemiSem screening. So the final part of this is to move on to the structural analysis with EBSD, or electron backscatter diffraction. So the first part, if you think about it, we use the imaging from the electron beam and the imaging itself. Then you go and do the chemical analysis, either through screening or you do this automated in a something like a perception workflow. The last part, though, is to look at the structural information. And to do this, the EBSD technique, typically you would tilt the sample. And what happens is, as the electron beam interacts with the sample, a proportion of this signal will be coherent. And because of this, you'll get a diffraction pattern, and the software is able to automatically identify or solve that diffraction pattern, work out the orientation, and then go on to the next point, the next point, the next point, to build up a map within the image. And because you're doing this, again, often many thousands of times a second, in a few minutes, you're able to build up quite a detailed map that tells you the full structural information. So into the next slide, what you're able to see is essentially the sorts of information and how this maps through to the challenges. So we're able to identify crystal phases, we can reveal degradation mechanisms, we can understand the grain size, the pathways, and we can link this to the chemistry through the technique that we showed earlier. And again, there are lots of challenges for batteries. They're complex multi-phase. There often can be quite a lot of the sample preparation. So again, really linking through the clean mill, the inert transfer. These things can be beam sensitive, so you want a system that works well at the low kV. And as we said, you've got complex and fine microstructures, so you need to be able to acquire the patterns and then index them really well. So onto my penultimate slide. This is sort of what you would typically see in a battery application. So on the left, you're seeing the secondary particles within the type of NMC. We analyze this. In this, you can see the individual patterns. You can see essentially the individual grain size. The kernel average misorientation is very helpful because this enables you to see how the localized stress will accumulate. And on the right, you can see the orientations of every single one of those secondary particles. And the diffraction pattern you see in the middle is what you're getting from this. And because these are trigonal, you kind of need nice patterns to be able to do these. And this is what you're able to now achieve with a modern EBSD system. So with that, I'd like to go on to my final slide and just sort of wrap up the analytical story. So what I'll say is the analytical, SEM-analytical techniques really enable this multifaceted characterization of the battery material. So the EDS, the phase mapping of the chemiphase, enable the composition. We can look at the spatial distribution, the chemical phases, and we can see small impurities that may be present. Particle analysis automates this whole process. So that's the automated quantitative characterization. And finally, the EBSD provides that local structural information, linking the crystallography to the wider picture itself. So these are complementary techniques in the SEM and the dual beam that gives you a greater understanding of your battery material. And with that, I'll hand over to Hsiang-Han.
Okay. Okay, so thanks, Chris. My name is Hsiang-Han. I will be talking to you about how we can use XPS to also help us understand the battery materials. Next slide, please. So before we get into how XPS can help us, I would just like to spend a few minutes introducing you the technique, just in case that those of you who are just encountering this today. So XPS is the core technique on our surface analysis instruments, which stands for X-ray photoelectron spectroscopy. And it's a way of measuring the composition in the surface of a material. You may have heard of it or come across in literature that some people call it ESCA, and that would be electron spectroscopy for chemical analysis. So basically, XPS involves exposing the materials to a beam of X-ray photons, and the interaction of the X-ray photons with an atom can cause emission of electrons. And because electrons interact very strongly with the matter, so when the electrons travel, they can only travel for very short distance, around several nanometers before they lose all of their kinetic energies. So that is basically the underlying principle, makes XPS very surface sensitive and also gives rise to an analysis depth of typically just around 10 nanometers thick. Now, the instrument itself measures the number of the electrons emitted at the particular kinetic energy and to produce a spectrum where then the peak areas are proportional to the amount of material, to the amount of element present in the sample. So that's very nice, but what makes this technique particularly useful for us is that the changes to the chemistry will directly affect the binding energies of the electrons in the atom, which we then detect as changes to the kinetic energies of the electrons emitted from the surface. And so in this way, the peak for a particular element will move accordingly depending on the actual chemistry of the surface that we look at, and that enables us to measure the composition of the sample. Next slide, please. So knowing these are the capabilities from the XPS, it's very clear that it provide very useful information on several key application areas for the cell R&D. So you can see this can be, for instance, using to check the surface quality of the raw materials and to investigating the cell components after cycling. Here is the list of application areas that our lab has dealt with. And I would say quite often we would use it to check SEI investigation after the cell disassembly. Next slide, please. In terms of XPS systems, because they operate on the ultra high vacuum, so when we do the analysis, there's actually no issue with air exposure. But then as we previously see before, that we still need to transfer samples. So this is a process that still needs to be air-free. On some of our systems, we can use Clean Connect, but then there's also an alternative, which is a vacuum transfer module. It's essentially a special sample holder that allows you to load your sample under a lower vacuum. But then once it's loaded, you put it in the system and it will open again when it's pumping down. So on this slide, you can see the version of the sample holder that we use for our K-alpha, Nexa, as well as HyPulse systems. Next slide, please. So during the XPS, once the samples are in the system, the first thing that we would do is to take the survey scans. And because this is where we're going to start seeing what elements are present in the surface of our sample. Now, this is just an example that shows the two samples from pristine and used cathode samples, materials that were being analyzed with the XPS. On the right-hand side, there are a survey spectra collected from the as-received cathode samples. The cathode material is based on lithium, nickel, manganese, cobalt oxides prepared by using a binder medium to hold the material together. And then the binder itself is based on a mixture consisting of a fluorine and oxygen polymer. And you see that for the pristine sample, it's quite evident that there's a significant residual that's amount. And then from this electrolyte, from the binder. Okay, so we can immediately see the difference between the two conditions, and we can then relay, because this may be important for the first use of the cathode. So for example, say if the binder it becomes mobile in the electrolyte, or it can react and then form some formation of the surface layer that impedes ion transport later on. And then in comparison, the used cathode sample is actually come from a cell that had been through several charge and discharge cycles and was in a charged state when the cell was disassembled. On the figure on this right-hand side of this slide, you can see the relative intensities of the manganese, cobalt, and nickel components, which appear to be quite similar between the two samples. However, you can immediately notice that the lithium component actually appears to be quite a bit less, so corresponding to around 40% compared to that seen in the pristine cathode. This behavior actually turns out to be very expected in a sample taken from a charged cell, because where the higher lithium concentration should be associated with the anode rather than the cathode, as also reflecting from a depleted lithium level compared to the pristine cathode. Next slide, please. But it's one thing very interesting and useful in terms of looking at XPS is the shifts in the XPS peaks. So these kind of shifts you can expect in the lithium 1s spectrum as well, and that obviously depends on the actual chemistry. So I'm showing you the samples taken from the metallic lithium, lithium oxide, as well as hydroxide, and you can notice that these kind of shifts appear in the binding energy, and it's exactly why it makes it possible to quantify which element that you have, but also you can really see the actual chemistry. So in this case, the chemical states. That's pretty good with what you can do with the XPS, but there's just one thing we should remember. In the XPS, we only have one peak for the lithium. So if today you expect there's a peak coming from another element that potentially overlaps, then in terms of treating the data, you will have to do some peak deconvolution carefully so that you can actually resolve the lithium chemistry. Next slide, please. So that's just very typical with XPS, but I would like to just add an example that we can actually do in situ experiments as well. And that's very exciting if you think about that. You don't just look at your battery materials, you can also apply bias in situ. And so here is a case. We actually perform in situ electrochemistry experiments, but do remember that the electrolyte will have to be UHV compatible, such as the kind of ionic liquids used in this study, and you can find the actual reference. On the left-hand side are the schematics that shows the kind of setup you need. So basically, you need to have a very small cell, well, smallish, and then that is made where the working electrode is here made of aluminum that could be mounted at the very shallow angle. So at the figure shows here. And this, you need to do that so that the electron electrolyte boundary can be measured. And then this can actually be confirmed by collecting the data across the line. So along the line indicated by the multicolor arrow, and choosing a point where you can obtain the signals from the electron and electrolyte, just two separate places, and then you can actually start doing it. So moving on to the next slide, you will see. So that's here are the figures. They were actually spectrum collected during the entire cyclic voltammetry experiment. Figures show here you can correspond to the peak maximum, and they were plotted as a function of experiment time. Then again, reflecting to the sweeping voltage that is being used during the experiment. And you can see that when we apply the bias, we introduce the shift for the electrolyte components, but not necessarily on those elements bound to the electrode. So when the cell is being cycled, it's very obvious, it's very clear here. You can see the intensities for the sodium and fluorine surface components appear to increase, and which are actually irreversibly bound to the electrolyte. So with this whole setup, we could say that this is basically a similar equivalent to watch the SEI form in the XPS system. And that's very exciting. I would recommend you to check out the reference. So can we move on to the next slide, please? So that's very good with what XPS and that we can see from the surface. But we also understand that many times there's even more interesting chemistry happen underneath, below the surface. So this is the point where we need to think about, can we come up with a method to look through into the sample? And we can. So this basically can be done with doing depth profiling. Essentially, doing a depth profiling is as follows. You take a spectrum of the surface of your sample, and then you remove some material, and then take the spectrum again on the new surface, and then altogether you then create a composition profile from the surface into the bulk. So in the next slide, I can show you an example of this. So from the very beginning, originally, when people looking at this, they develop using monatomic argon ion sources to remove the material, to do the depth profiling. And then, but for some time, it has been shown that it's actually has some small problems. Sometimes it can introduce some chemical changes to the remaining material, obviously, depending on the kind of material you're working with. But the end result is that when this happens, you get the profile that is not very, that doesn't reflect to the true material, so it's distorted. And because of the reason, people then move on and trying to develop argon cluster ion sources. So using the clusters rather than the individual ions to bring a gentler effect. So in the hope that we can limit this kind of problem, to solve this problem. And it is true that this method has been quite successful and work well for a range of materials, including the polymers. So here, it's an example to show that we do the depth profiling for the proposed electrolyte for solid-state batteries, which is lithium, phosphorus, oxide, nitrides. And on the right-hand side is the monatomic profile. You can see that there's suddenly a very sudden increase for the lithium concentration just at the interface. And the reason we are getting this kind of behavior can be explained by using the monatomic bin that basically sort of push the ions. And as the lithium ions just hit at the interface, it just couldn't go anymore. So that's why you get a small increase just on top of the substrate. But on the right-hand side is the result when we try to use cluster ions. And it's true that we no longer have this kind of damage, and the profile is more accurate now. But the next slide, please. But that is okay. I mean, it's a very nice improvement when we switch to do cluster ion profile. But then we still need to remember it actually doesn't work for all the materials. And in particular, over the years, it has been shown that the cluster sources don't work that well for a certain number of inorganic materials. Because of this made me try to look for another, try to find a solution. So we recently introduced a new method and to do depth profiling, and by using a femtosecond laser as a source to do the material removal part. And it actually has the advantage of not introducing chemical changes to the samples. But then at the same time, because it's femtosecond, it makes the whole experiment times much shorter and make it possible and easier to collect a whole lot of series of profiles. But probably more exciting thing for us is that recently we've seen that this approach is quite suitable for looking at battery materials. So in the next few slides, I'll just show you example before we conclude. Thank you very much. So now I'm presenting a battery sample from MIT at the University of Münster in Germany. It's a lithium metal electrode and has already been cycled. Our goal is very simple. We want to understand the chemistry of the SEI layer formed on top of this electrode. So there's no other way. We have to do the profile through the layer all the way to underneath to the underlying metal electrode. In the first place, we try with monatomic argon ions. And here the figure shows you the evolution of phosphorus chemistry. You can immediately notice there is an additional feature that start emerging just after the first cycle of monatomic ion etching. It's a strong indication that there's some ion beam damage going on to the sample, and it already happened after the first ion exposure. So the next slide, you will see how obviously this is not great. So we then try to do cluster ions because that should give us a slightly gentler effect. And it is very gentle. So if you focus on the lithium spectrum, you will see that it looks like we're just always hitting the same surface, despite that there's no chemical damage can be observed. So because what we would like to see is to see some concentration, contribution from the underlying metallic lithium, and we don't see anything. So this probably means the etch ray is not sufficient to go through the SEI layer. But the next slide, you will see our latest development. So as we switch on to do femtosecond laser available on the HyPod system, now we can actually depth profile through the SEI layer. So as you can see, this changes is quite apparent for the lithium and also for the fluorine. And the composition can be measured accurately, more than using previously either ion beam approach. But what is very exciting to see is that the laser profile shows that the lithium fluoride and other components can be removed consistently, revealing the underlying lithium substrate or the electrode. We know that it's not possible before when we just try to use the cluster ion etching. also, the removal of the organic fluoride can be just obtained without chemical damages from what we can see here. So in conclusion, we think the Fessler femtosecond laser profiling opens a new route for analyzing battery electrodes, and it can definitely help us again a deeper insight in terms of how these layers form and grow as the cell ages. So I will just quickly conclude. Hopefully, I'm just showing you a few examples in this quick tour, how useful XPS can be when it comes to analyzing the battery materials. So you see from all the way determining the elemental compositions at the surface to probing into the material and reveal very complex chemistry, composition changes, and I personally think XPS is definitely a very effective tool for understanding electromaterials and other solids also used within the cells, for example, such as separators, contacts. And moreover, I include an example that we can perform in situ experiments, operando studies. That's also possible as long as you put some thought into the experiment design. So the last slide, yes. So if you would like to find out more information, I guess you just go to the link and then you will see more information. Yeah, so thank you very much for your attention. That's what I want to say about the XPS for battery analysis.
Perfect. Thank you, Hsiang-Han. And thank you for those who are staying a little past the 1 hour time mark. Lots of really, really valuable and interesting information here. It's always impressive to me to see how far we've gone from trying to transfer samples over very quickly into glove box, calling that air-free sample transfer, and also the days of using ImageJ. We have a lot more sophisticated technology today. We have quite a lot of questions here, and we'll be able to answer a couple here live today, but I just want to let people know that if you answer a question in our Q&A chat, then we'll be able to follow up with the Thermo Fisher team after the session.